And OBS is recording, and here's the clap take. Go!
Oh, hi. I'm Adam. I'm here with Brian. How you doing, Brian?
Hi. I'm great.
Great. All right. I thought we would look at a question and learn a little bit of trigonometry along the way. So I've got a picture here of my wonderful half sketch here of the Earth orbiting the Sun. And the question I had in mind was, well, how fast does the Earth orbit the Sun?
Relative to the sun?
Yeah, relative to the Sun, of course.
Yeah.
Yeah, of course the Sun's moving, and we're rotating on the Earth, so there's lots, but just simple, how fast is the Earth orbiting the Sun?
Cool.
Have any idea?
I feel like 60,000 miles an hour or something crazy.
That's pretty
like
guess, yeah. We'll be able to kind of get a better, little bit better number on that.
Okay.
And maybe we'll figure out some trigonometry along the way.
Sweet.
So let's take a look at that. So there's really two things I want to look at. The first one is arc length, and then we will turn that into a discussion on linear speed and angular speed. So we'll kind of get an idea of how fast the rotation is of the Earth around the Sun. Is not as hard of a problem, and then we'll figure out how fast the Earth is moving. So let's start with that.
Cool.
So arc length. So we've got a circle, and we're interested in the length of an arc. So if we have an angle, let's make it a central angle.
Does that just mean it starts at that?
Right, the central angle
Going
is
straight, right?
an angle where the vertex is at the origin, or
Okay.
not necessarily the origin, but the center of the circle anyway.
Okay.
All right, and we'll give that angle of theta, and then the arc length is this. So it's the S, and that is the part of the circle that's intercepted by the angle, right?
Uh-huh.
The part between the sides of the angle. Right, and the question is, how long is that? How long is S? Given an angle, can you talk about how long the arc length is? Right? And you already know one, right? You already know the whole distance around the circle.
Right, so if it's 360 degrees angle,
Right.
then you've got pi r squared.
That's the area.
That's the area,
Right,
so
I'm
then we're just talking about the circumference.
Just walking
which is
around
pi.
the edge. Well, it's
1 pi.
not 1 pi. Do you remember the circumference formula?
Nope.
That's okay.
Apparently not.
It's 2 pi r.
2 pi r.
Yeah. So if we have a whole, I'm going to put a little table together here. So we've got rotation, the angle that corresponds to that rotation, and then we'll look at the arc length, right, for that rotation and that angle.
Okay.
So if we go all the way around the circle, right, so we start and end at the same point here on the circle, we'll have swept out an angle of 360 degrees, as you said, right? Now, for arc length, we need to use the radian measure. So what is 360 degrees in radians?
2 pi?
2 pi, right. Okay, and then the arc length, well, it's just going to be the rotation around the circle. So there's going to be some radius for the circle, and we take 2 pi r, and that will be the arc length. Right?
Okay.
So point starts here. If we want to move it around the circle, ends up here. It travels a distance of 2 pi r.
Okay.
All right. Okay, let's take another angle. What other angle would you like to see, or what part of a rotation here?
Well, let's do 90.
Yeah, let's do 90, okay. So 90, right, that is a quarter rotation. What angle corresponds to that? Well, 90, right? And in radians, that's?
It's going to be 1/2 pi r? 1/2 pi?
Yeah, 1/2 pi, exactly.
Okay. Pi over 2.
Right, and then what arc length would correspond to that?
Well,
Well, just think about it this way.
So
The
pi
whole-
radius over 2?
Yeah, pi r over 2. That's right, yeah. You think about it in terms of the whole is 2 pi r,
Mm-hmm.
and we're taking a quarter of it. So we divide by 4.
Oh,
right?
okay.
Yeah, so 2 pi r over 4 is pi over 2 times r. Yeah.
This is nice when you can leave math in a readable format instead of you always have to subtract to the minimum term every time. That's nice.
Right, yeah.
We'll leave the simplification for the end.
Yeah, exactly.
Okay.
And we want to see the parts, and we put the parts together, and you see how the parts put together, and then you can simplify it to something that you can put in your pocket and take with you. So that's
Right.
one way to put it. Let's do one more. So how about the half
Okay.
circle? What angle corresponds to?
So that's 180 degrees.
Right? Or
A pi.
pi, yeah.
A pi
Yeah, I mean,
radius.
you got the whole, right? Divide that by 2, you get pi. Yeah, good. And then the arc length?
It's just going to be pi times pi r.
Pi r.
That's the arc length you said?
That's the arc length, right?
Okay.
The distance that, the length of the arc.
Okay.
Right. The whole circle would be the circumference, so it's the length, all right? If you were to fence in a circular area, that's how much you'd have to, how much fencing you'd have to have, right?
And just to reduce it to an actual, like, approximate term,
Sure.
if the radius was 1, that arc length would be 3.14.
Sure, yeah.
Okay.
If the radius is 1, then the arc length happens to be equal to the radian measured, which
Okay.
is where the radian comes from, actually. It's the definition of the radian.
Oh, really?
I thought we might do that in another video. So
Okay.
we'll come back to that. Okay. So let's kind of generalize this. So let's say we have just an arbitrary angle here on a circle.
Mm-hmm.
Right? Call it theta. Right? So that's theta here for the angle. What would be the arc length?
Wait for it. Is it 2 pi r over theta?
Well, no.
No, okay.
So angle, arc length. Angle, arc length.
Mm-hmm.
Angle, arc length. Angle.
No, go for it. I'm lost.
Okay, so for the angle of 360 degrees,
Yeah.
2 pi, right?
Okay.
And then to get the arc length, we go 2 pi r.
Okay.
For the angle of pi over 2, quarter rotation, the arc length is pi over 2 r.
So in radians, which is is that what we always use?
Yeah.
Okay.
For arc length, for applications involving arc length, we'll always use radians.
So it's going to be theta times r.
Theta times r.
Okay.
That's right. That's right.
Okay, that's really easy.
Yeah. So the arc length formula. So we've got a circle of radius r. We sweep out a central angle here of theta. The arc length is given by r times theta, or theta times r. However you like. Multiplication.
Cool.
However you like. Okay. Great. Okay. So now we have an idea of distance around a circle. Right. Start at one point, walk a little bit. And somewhere we can calculate that distance. There we go. All we need to know is the central angle that's swept out and the radius of the circle. Okay,
Okay.
let's talk about motion in a circular path. So you are already familiar with the distance formula, right? Or the distance, the typical physics equation, right? Distance equals rate times time.
Okay.
Um,
I've used that before.
Yeah, so the rate, let's solve for the rate. So the speed, let's say, is the distance over time, right? It's the distance traveled per unit time, right?
Right.
So you've done this before, right? Travel, 300 miles in, 6 hours, right? Speed was 50 miles an hour, right?
Mm-hmm.
Okay. So the distance, we're going to look at a distance around a circle, right? So the speed, we'll call it v, is going to be some arc length swept out per unit time.
Okay.
This is the expression for the linear speed of an object traveling around a circle, right, in a circular path. S is the arc length. T is time. and v is the linear speed. Okay. We also have an idea of angular speed. Angular speed is given by this symbol, which is a...
It looks like W.
It looks like W. It's a omega.
Omega.
Lowercase omega, yeah.
Good to know.
And in the same way, we take a distance divided by time. If we're looking at an angular speed, we're talking about an angle swept out per unit time. So we'd have our theta divided by time. So theta is the angle, right? And t is time, right? It's just the time that it takes to sweep out an angle of theta.
Okay, I'm confused. We've got angular time, and we've got linear time. Not linear time, but linear speed.
Speed, yeah.
And we're still using an arc length for speed?
Right. Well, we're talking about circular motion, right? So something moving in a circular path.
Okay.
Like the linear
the
speed, yeah.
Okay.
Yeah, just like the Earth, orbiting the sun, right? We'll have a linear speed, so it'll move a certain distance around the circle, that's the distance, right? In a certain amount of time. So, and that's how fast it's going, right?
Okay.
So it's always distance divided by time. So
the other thing we're measuring is how fast it's rotating.
Rotating, right.
So, okay, the number of degrees rotated per length of time.
Yes, exactly. Yeah, and that's theta divided by t.
Got it.
Only the theta is going to be in radians, right? You could convert it to degrees, of course, so we'll probably do that.
Okay, number of radians over time.
Yeah, radians per unit time.
Got it.
So I guess for a quick example here, if you have a clock, right? Right, and we have a second hand, right? This second hand has an angular speed, right, of, well, we'd have 2 pi, right, over, well, it depends on whatever time unit you wanted. If we're talking about, say, minutes, right, it would go 2 pi per minute, right, because it goes around a hole every minute.
Okay.
Right? So, so we could say omega is 2 pi over 1, right, 1 minute for the second hand. If you like degrees, you could say 360 degrees per minute. That would be the angular speed.
Cool, I got it.
Yeah. If we're interested in, say, how fast it moves per second, we could just convert this to seconds, right? So that would be, 60 seconds is 1 minute, right? And we could say that 6 degrees per second, right? So when you're looking at a clock, every tick of the second hand is 6 degrees. Right? Cool. And then 60 of those is 360 full trip around the circle. Right?
Got it.
All right.
Awesome.
Okay. Now, the linear speed formula and the angular speed formula relate, as in we can go from one to the other. Notice S here is the arc length. What was the formula we had for arc length?
S equals the radius times theta.
Right. So S equals r theta. V is S over t, but S is r theta.
Okay, so yeah, V equals r theta over t.
Yeah.
Okay.
And now in that ratio, in that fraction that we see there, do you see something else we talked about?
Rate over time? No, that's different.
Well, yeah, over time, that's important. How about the theta?
Over time?
Yeah, what's that?
That's our angular speed?
That's our angular speed, right. So we can write the linear speed in terms of the angular speed.
Okay.
R times omega.
Huh.
Right? So this right here becomes the omega, right? And then we just have the factor of r, right? So the linear speed relates to the angular speed through the r, the radius of the circle.
Okay.
So you take your angular speed, multiply by the radius of the circle, right? You get your linear speed.
Huh, well that's pretty easy.
Yeah.
Okay.
Yeah. So this gives us now what? 4 formulas. I'll put the angular speed back on here. That relate to circular motion, right? Speed around a circle in a circular path. We have the arc length formula. Doesn't involve time. It's just distance. We have the linear speed. We have the angular speed. And then we have the relationship between the linear speed and the angular speed going through the radius. Okay.
Sounds
I think
good.
we're equipped now to tackle the Earth orbiting the sun.
Yeah.
Okay. So let's get some facts down. So we're going to assume that the Earth's orbit is circular.
Perfectly circular.
Right.
Which I don't think it is, but
No. It's
for our
not.
math,
Yeah. For
way easier.
we're just getting an estimate here anyway.
Cool.
Yeah. So the orbit is circular.
And does that mean it's a central angle?
Yeah. The sun being at the center.
Okay.
Yeah. Right. So if we were looking from the sun, right, out to the Earth, right, that would be one of those sides of the angle, right, and then that sweeps out as the Earth orbits. Right? Okay. So Earth's orbit is circular. Sun is at the center. The radius would be the distance of the Earth to the sun, from the sun to the Earth. And we're going to just take that as an even 93 million miles.
Okay.
And we're also going to make another assumption. Since we're interested in speed, we need a time unit, right? And we'll assume that the Earth orbits the sun in 365 days,
Okay.
which it doesn't.
Do you want to add the 0.25?
No.
Okay.
Because we're rounding the radius to the
That
million
much, okay.
miles,
I
so
gotcha.
it's not going to matter. We're only going to get 2 digits here, significant digits in our answer anyway. Okay, so 365 days per rotation, per orbit. Okay. That's all we need now.
Okay.
So the first thing we should start with is the angular speed of the Earth. So the angular speed of the Earth, remember, is angle swept out per unit time. So you could easily write this down.
So that's omega equals 2 pi over 1 year.
Yeah, 1 year, right. How about in days? What would it look like?
365 days.
Exactly.
Okay.
How about in hours?
So divided by 24.
Not divided by
Well,
24. There's 24
times
per day.
24.
Right, so
Right,
20
okay.
times 24, right. So 2 pi over 365 times 24, and that will give you in hours. Yeah.
Which I'm going to look up.
Yeah, go ahead.
Calculate. 365 times 24. It's 8,760.
8,760. All right. 2 pi over 8,760. I'll just put hours in there. All right.
Okay.
Great.
That's our angular speed.
That's our angular speed. Now, we wanted to go to linear speeds. How fast is the Earth orbiting?
Mm-hmm.
Well, what do we do?
So V equals radius theta over t time.
Sure. But theta over time is...
Or V over S of t.
Right. The last formula we looked at, right, is V equals R times the angular speed.
Which is 2 pi
Which is omega.
omega. Oh, that's right. I didn't write that one down. What was that one? V equals RW.
Yeah,
Okay.
V equals R times omega. Right, this is the one that relates the angular speed to the linear speed. So
Okay.
we found the angular speed.
Mm-hmm.
All we need to do is multiply by V.
Radius.
Yeah.
Okay. So that's V equals 93 million.
Right? And then times what you calculated over here, 2 pi over, 8,000...
8,760.
Yeah. Oh,
Whoops.
bring it back. All right.
Undo works like that?
So it looks like this.
I did not know it did that. Man. Okay.
8,760 hours, right? And that's great. So the 93 million's in miles, right? We've converted the angular speed to radians per hour.
Which is why we're doing hours, because we want miles per hour.
Right, because we want miles per hour. So this, what we have written down right now, will give us miles per hour. So go ahead and use your calculator. Go ahead and put all those together.
Okay, so I can put these in
93
here.
million times 2 pi, and then divide by 8,760.
Okay. Where is pi? There it is. 2 pi divided by 8,760. And enter. And I get 66,705.
Yeah, let's round it to 2 significant digits.
So 67,000
67,000 miles per hour. Yeah.
Okay.
Yeah, so your guess about 60,000 miles an hour is pretty good. Okay.
Awesome.
So 67,000 miles per hour.
Okay.
All right. You feel it? You're
Yeah.
moving that speed right now.
No, not right now.
Not right now. Okay. Well, there we go. Okay, so of course the applications of this go well beyond just Earth orbiting the sun. I mean, anything that moves in a circular path. We can talk about how fast it goes. Things that come to mind are like tires, or if you have a pulley for a belt, right? So in a machining factory, right? The product's being moved along along these tracks, right?
Mm-hmm.
And belt, right? And the belts are turned by wheels, right? And so the angular speed of the wheel, right, is going to translate, and the radius is going to translate into some linear speed, right, of the product or whatever moving along the belt, right? Think of an airport and your luggage, right, gets moved along like that, right? So there's all kinds of applications. I mean, tires, you think about that. I mean, this turbine on an engine, I mean, all over the place this shows up. And these are just the basic equations that tell you about it.
What's the linear speed of a jump rope?
Yeah, sure, yeah. Yeah, a point on a jump rope, right,
Okay.
going around, yeah.
Huh.
Yeah. Endless. All right. Yeah, let's just review then. So we have the arc length. That is S equals R theta for central angle theta in radians. Right? Important to remember that. Nothing wrong with degrees, you just have to convert to radians.
Mm-hmm.
We have the linear speed, V, and that's arc length per unit time. We have the angular speed, the funky W, the omega, theta per unit time. And then we have the equation that relates the two, right? That the linear speed is R times omega.
What did you call that last one?
That's just the formula that relates the linear
How it
speed and
relates.
angular speed. Yeah. Yeah, so if we want to go from linear to angular, or vice versa, right? So it's kind of the exchange rate between angular and linear.
Okay.
All right.
Cool. I like it. Can we do one more?
Yeah, sure.
I don't care which one you pick. It's kind of thinking how fast a sling that you're swinging around, and then when you let go.
Okay.
Can we do something like that?
Yeah, sure. Yeah, let's try that. So we've got some sling, right?
Mm-hmm.
Right. Let's say so we're sending it around like this.
Mm-hmm.
You can imagine that. Right?
Mm-hmm.
Okay. How long do you want the sling to be?
Can it be 1.5 feet?
1.5 feet. All right. So 1.5 feet, half a meter. Right? And then we need some angular speed. So we need to think about how fast the sling is going around.
So can we do it 2 times per second?
2 times per
Does that
second.
seem reasonable?
Yeah, sure.
Okay.
Twice a
Or
second.
once per half second. You know what?
Yeah.
however you
Okay.
wanna
So
say it.
2 rotations per second. Right. That's a good way to put it, because that's something that we can easily kind of see or measure, right? Get a video of it. You could count the number of rotations, right?
Mm-hmm.
And then to go to, say, a linear speed, which I think is what we're headed towards.
I don't know how fast it goes when I let go.
Yeah, exactly.
Yeah.
That's going to be, we need to convert that to radians, right?
Mm-hmm.
Which is not too bad, right? 2 rotations per second, right? converts to
Maybe
radians.
4 pi?
Yeah, 4 pi.
Yeah.
Radians per second. Right? And now, the last formula we looked at, right, the one that converts between the two,
Mm-hmm.
V equals R times omega, and we just found omega.
Because omega is 4 pi over second?
Yeah, it's the angular
so
speed.
easy.
Yeah.
Okay, this is omega.
Yeah, and so the linear speed then would be the radius, 1.5 feet,
Okay.
and then omega is 4 pi per second.
So velocity equals 1.5 feet times 4 pi. Basically just 4 pi, right? Because it's over 1.
Yeah, 1 second, right?
Okay. All right. So 1.5 times 4 pi equals 19 feet per second.
Sure. Yeah, let's just round that to
20?
feet per second.
Yeah. It's 18.849.
Oh, 18.849?
Yeah.
That would round up to, 20.
Still round up to 20.
Well, because we're saying there's just 2 rotations per second, so that's 1.
One
Right,
unit
just-
of,
yeah.
what'd you call it? One
Significant digit,
Significant
right.
digit.
Just-
Okay. Equals.
We're just getting an estimate anyway, so
Yeah.
20 feet per second.
And so it's just a matter of changing the things up to be miles per hour.
Oh,
okay?
sure, yeah, we could do that too. So 20 feet per second, and then we need to convert that to miles per hour. So, like 1 mile is 5,280 feet, so that would be miles per second now.
Okay.
And then we need to convert the seconds to minutes, right?
Mm-hmm.
So we know there's 60 seconds in a minute. And I always like to set it up like this because if you think of the units as variables, they would cancel out. Right?
Mhm.
So the feet cancels with the feet down here. The seconds cancel here. We're left with minutes. And then we want to convert that to hours, right?
Mhm.
So 60 minutes is 1 hour. So that will convert it to miles per hour. So 20 times 60 divided by 5,280.
Got it. That's what I put in.
Yeah.
In different ways. That's a
Yeah,
nice way
yeah,
to
sure,
look at
yeah.
it. And I got 13 miles per hour.
13 miles per hour. Okay.
Cool.
Yeah, so about 13 miles an hour.
I don't know if that's fast enough to hurt.
It's probably spinning faster.
Than that 2 revolutions per second.
Right,
Yeah, you're
right,
probably
right.
right. And it's, if it's a marble at 13 miles an hour, that might hurt a little bit.
Sure, yeah.
Okay.
But so it's very easily to apply to any situation where you have something that's rotating.
And it's
So it
nice
goes
to
down.
know that I've already kind of got an idea of how many, that angular speed.
Yeah,
Angular speed's something we can calculate most of the time.
sure, yeah.
Rotations per
Count
second.
rotations, right.
Okay.
Yeah, and then if you know the radius, boom, you've got linear speed.
Cool. Awesome. Thanks.
Great, awesome. All right, I'll see you next time.
See you next time. And cut.
All right, that was good.
Yeah.
What do you need?